The mechanical reality of 3D printing is that it creates objects layer by layer. Fused deposition modeling relies on stacking semi-molten thermoplastic filaments. Because the material is deposited in continuous stacked rows, rather than molded as a single solid mass, FDM generates parts with inherent physical directionality. This structural anisotropy makes it difficult to predict how a part will behave under mechanical stress, heavily restricting its use in load-bearing manufacturing. To find the exact failure points of these printed polymers, researchers apply the ASTM D638 standard, pulling specimens apart in a universal testing machine until they snap. This chart maps the true stress versus true strain curves for PLA, ABS, and CPE. The wide variation in performance within each material is driven entirely by how the part was printed, requiring precise control over the internal microstructure. That control depends on 4 specific target variables during extrusion: layer thickness, raster angle, infill density, and nozzle temperature. These variables interact with each other nonlinearly. Changing the layer thickness alters how heat transfers from the nozzle, which in turn affects how well the infill bonds. Simple intuition is insufficient to optimize the resulting structural integrity. To predict how a part will survive under load, we have to analyze exactly how manipulating these parameters physically alters the micromechanics of the polymers. Isolating those physical mechanics is the necessary precursor to training an artificial neural network, a computational model capable of predicting the ultimate strength and ductility of an end-use part with 97% accuracy. To isolate the variables, researchers structured a Taguchi Design of Experiments, executing a systematic series of test prints across the PLA, ABS, and CPE materials. These main effect plots track how each physical printing parameter influences the ultimate tensile strength of the specimens. The data isolates the dominant impact of mass density on structural integrity. Increasing the infill density from 40% to 80% boosts raw tensile strength by 27% in PLA, 30% in ABS, and nearly 56% in CPE. Beyond simple mass, orientation governs how the part bears a load. The raster angle, the direction the nozzle travels while filling the interior, dictates the part's capacity to resist tension. Across all 3 polymers, a 90-degree raster angle provides the absolute optimal orientation for maximizing tensile strength. The performance gap is massive. Orienting the toolpath to 90 degrees outperforms a 0-degree angle by 47% to 52%, depending on the plastic. In stark contrast, parameters like layer thickness and nozzle temperature barely register an impact on ultimate tensile strength in these tests. The physics behind this are straightforward. A 90-degree angle aligns the continuous, unbroken lines of extruded plastic parallel to the tension load, optimizing the distribution of force along the length of the fibers. When engineering a polymer for pure tensile strength, toolpath alignment and internal mass density are the primary microstructural levers. Thermal parameters are strictly secondary. Maximizing rigid strength is only half the engineering equation. Certain parts need to yield and stretch before snapping. We have to pivot to measuring a part's elongation at break, or its ductility. These main effect plots track how the exact same printing parameters influence elongation. The response is completely inverted. The 90-degree raster angle that maximized rigidity now yields the lowest possible ductility. The optimal parameter for elongation shifts to an alternating 45 and negative 45-degree raster angle. Applying this alternating angle improves ductility by 47% for PLA, 80.5% for ABS, and an astonishing 104% for CPE. This data motes directly to the internal structure of the print. When a tensile load is applied, the alternating cross-hatched layers facilitate controlled shear deformation. The matrix absorbs the energy, allowing the individual layers to slide and stretch slightly across the print volume. A 90-degree orientation locks the fibers in place, resulting in a rigid, brittle failure. The alternating layers distribute the strain. Ductility in 3D printed parts is an engineered mechanical feature. We force the toolpath to absorb energy through internal shear dynamics. With the physical mechanics established, the challenge is building a predictive tool. Physical variables like layer thickness and temperature interact with the infill and raster angle in complex, nonlinear ways. Standard mathematical equations struggle here. Sixth-order polynomial and exponential regression models applied to this dataset yielded low predictive correlations, failing 32% to 57% of the time. This schematic maps the computational solution, a feed-forward artificial neural network. The network uses a Levenberg-Marquardt algorithm combined with backpropagation to optimize the weights of its connections based on the experimental data. The architecture receives 5 normalized inputs: the material type, layer thickness, raster angle, infill density, and nozzle temperature. Those inputs feed into a hidden layer consisting of 9 distinct neurons. This hidden layer applies a tangent sigmoid transfer function, processing the complex, nonlinear physical relationships we observed in the parameters. Finally, the network synthesizes these interactions to generate a single output targeting ultimate strength or ductility. This architecture effectively acts as a digital twin for the printer. It simulates the physical shear and load behaviors established on the testing rig. These 4 regression plots visualize the network's predictive validity for tensile strength, mapping the model's predicted values directly against the actual physical test targets. The correlation is exceptionally tight, achieving an overall R value of 0.97498. A second network trained to evaluate a part's elongation at break yields similarly precise regression plots. The ductility model tracks with an overall R value of 0.94293. Traditional mathematical models failed to predict polymer behavior up to 57% of the time. The neural network predicts structural outcomes with 94 to 97% accuracy. FDM parameters dictate physical mechanics. By pairing a rigorous physical design of experiments with artificial neural network mapping, additive manufacturing abandons rapid prototyping guesswork. It becomes a system for highly predictable, load-bearing component production.